Welcome back, everyone. So this talk is going to be an overview of probabilistic programming in Julia. It's going to be a condensed version of our earlier detailed talk. And let me just quickly introduce myself. I'm a research scientist at Juliahub, and I have some prior experience with probabilistic programming by being able to contribute to Turing.jl and Julia Gaussian processes, as well as being able to work with Gen.jl for my undergraduate thesis. So let me take a deep dive. Let me first motivate Bayesian or probabilistic ML by kind of comparing it with deep learning. So with deep learning, we always want to have deterministic models, and deterministic models are considered sufficient to model any given real world scenario, and it is filled with deterministic computations, and the main thing you try to do here is minimize loss. So there's a loss computation which is happening, and we often use automatic differentiation to minimize that given loss using some sort of an optimization technique. In contrast to this, Bayesian ML believes in representing each of real world happenings using random variables, probabilistic random variables, which are each kind of assigned or sampled from some sort of a prior distribution, and every relationship between random variables is there are a bunch of probabilistic relations. That is, it is often a sample of some sort of a distribution. There could obviously be some deterministic computation happening in between, but the overall objective here is to get a distribution and not a single deterministic value. And what is important here is to approximate the distribution of interest, which is called a posterior. We'll come to that in a second. And the main thing we use to do that, the tool which we use to do that, is inference, and unlike optimization and deep learning. So let me kind of preface this with an example model. This is a golf model where a person's variance of shot and variance of distance are treated as random variables. So that idea in any probabilistic model is to be able to have a worldview and kind of integrate your worldview into this sort of a graphical probabilistic model, where the different variables in your environment are treated as random variables with different distributions as their priors. So here you can see that some of them are deterministic computations. You can see that P good angle is a deterministic computation, but there's a probabilistic element to it, and the probabilistic uncertainty is sort of propagated through the probabilistic graph. So the most important theorem when it comes to probabilistic programming or Bayesian ML in general is the Bayes theorem, which is essentially states that given a kind of previously held worldview, which is a prior distribution, and you have some data which is encompassed using a likelihood, you should be able to compute something called a posterior distribution. So this posterior distribution is an updated distribution. It's prior updated with data. There's also a denominator called evidence, which is essentially an integration of the numerator with respect to y, which is often intractable and ignored, and you only care about the numerator and sort of the relative value of the numerator among different parameters which you want to estimate. So the next main thing which we will deal with is how do we represent the given generative or a probabilistic model as a code. It is often done in a declarative manner. That means essentially representing the whole model together. As you can see here, the entire linear regression model along with the priors with respect to different parameters are together represented in an at model macro, and this is often enabled through some sort of a domain specific language. In Julia, we enable this through the use of macros and powerful meta programming capabilities, and often at least in Julia, you will be able to use the full flexibility of the language within this model specification. This enables for a very high expressive power while maintaining the declarative nature which is required to convert this good looking or user readable pseudocode like code into actual underlying Julia code. So the main problem which probabilistic programming tries to solve is inference. Inference, if you try to hand derive it, is very hard and error prone, and even a simple linear regression which we saw earlier could take like half a page to 1 page of mathematical derivations, and that is often you'll end up making errors sooner or later. And the role of probabilistic program here is to automate that procedure and give a generalizable way to like produce inference code for a given probabilistic model. Yeah, so this kind of summarizes everything, and one thing to note here is that probabilistic programming languages try to combine the representative power provided by the DSL with the automated inference capabilities which the PPL provides. That's why it often ends up being the meeting point of programming language folks who are worried about semantics, and machine learning folks who are worried about really good inference and inference which gives good posterior estimation. Now we come to Turing.jl, which is the Julia package which enables probabilistic programming language, which DSL closely imitating Julia language, and even just pseudocode which you see in statistics papers. And the notation is quite similar. This enables for easy readability, but one main thing it offers is modularity, and it enables that by decoupling modeling language from inference method, unlike other programming languages like Stan. This enables one to incrementally add new inference methods as and how research progresses, and have a common modeling scheme irrespective of what inference procedure you use, and also develop the semantics of model representation independently. That is, you can keep adding new distributions to the whole like representation corpus. That way you will be kind of developing on two fronts independently, that is modeling front and the inference front. So Turing supports 4 main types of inference. Today we mostly cover MCMC because it's the most fundamental kind of inference which is important to understand. So how much time do we have left? 7 minutes. Okay, that's good. So the most basic kind of MCMC algorithm which we can use is the Metropolis-Hastings algorithm. What it essentially does is an exploration versus exploitation step within the probabilistic terrain of the posterior. So as you can see in this figure, you will see that all we are trying to do is you can see the green dot moving around. That's essentially the different points in the probabilistic or in the like density space which is being considered and either rejected or accepted. It's always accepted if it has a higher probability of occurring than the existing or the current parameter sample. Or there's also an exploitation step where you also want to take a risk and go towards a worse sample, just that in hopes of overcoming a kind of a local minima and going to a better global minima, right? Or exploring the entire space as a whole. So this is what Metropolis-Hastings is all about. It's a very simple algorithm which has a very simple way to kind of consider new points. It just takes a random point around the existing point and hopes that it's better. A more complex extension to Metropolis Hastings is the Hamiltonian Monte Carlo. Here, you don't rely on just trying to compute or trying to propose points near your current point. You actually try to consider points which are far away, and you do so by doing a physics simulation. You essentially consider the terrain of probability as a physical terrain, and you can consider the current point as like a ball, and you basically kick the ball in a random direction with some random velocity. This way, you can be more certain that you will reach far off places with good or more likely posterior samples. So this is computationally obviously way more intensive, but it is found to converge with fewer samples because the quality of samples is better. One more thing to note with Hamiltonian Monte Carlo is that it requires derivative information. So you will have to differentiate through your log density function, that is through your distribution. Only then can you use HMC. So it is not applicable for cases where you use discrete distributions where it's not differentiable. So with the remaining time, let me just quickly introduce you to the Turing docs. So Turing docs have pretty good introductions to just get started with very basic functions and how to go about using various different algorithms, right? So what we used Hamiltonian Monte Carlo is actually called NUTS. It's no U-turn sampler. It's an implementation of HMC, and you can play around with it here. And one thing to note with all of this is that for any given MCMC algorithm, it's always important to note the effective sample size. This is the actual number of credible samples or worthiness of your samples. So if the ESS is lower, that means that your inference method didn't work that well, and it's important that you tune it until you get a sufficiently high ESS so that you have credible posterior computations. And apart from this, there are more advanced usages where you can use different inference methods, like the one we mentioned here. One is particle simulation based methods, Gibbs sampling, and variational inference. And these are out of scope for this talk, but please refer to a larger talk for this. Okay. Yeah, so I can briefly talk about particle based inference schemes. So these particle based inference schemes are useful when there are multiple nodes which are hard to reach. And since exploration is not a problem here because you start from a wide variety of places parallelly, so your initial particles will be throughout the posterior space, and then you individually or parallelly converge all of them, like parallelly run all the chains until they converge to some sort of a higher density place. And this is great to do with multi-mode condition, but it's very computationally intensive and it might not be feasible in all scenarios. And within for each chain you can run something like Metropolis Hastings or even something more complex like HMC, but that depends on whether you have access to derivative information or not. Yeah, that's about it for today. Thank you.